Fine, guys. Just one moment, beta. All right. So guys, in the live chat section, please tell me if you can see me and hear me, beta. Because I think some technical issue is there. I'm really sorry for that. Can you guys see me and hear me, beta? In the live chat section, you can tell me. Okay. Okay. So some sort of technical glitch happened. Okay. All right. We'll continue. Okay. So we have this equation which is mostly used for taking care of the problem of related to continuity equation. So we have this equation, guys. We have this equation, and we have del u by del x plus del v by del y plus del w by del z is equal to 0. And this is also valid when the flow is only compressible, guys. It is also valid when the flow is only compressible. The flow is only compressible, right, beta? The flow is only compressible. Now, in this, if you see the questions of fluid kinematics from this zone, you will see two kind of a question. So, first kind of a question is first type. Let's suppose that type 1 question. So they will ask you, they will give you a velocity. So, okay, so they will give you some u, they will give you some v, they will give you an equation like this, somewhat equation like this. Okay, and they will ask you to check whether is steady and incompressible or not, whether is steady and incompressible or not. So how you are going to do it? You are going to take care, like for suppose, let's suppose we have x y I, x y z I, x square y square z square j. If our equation is like this, I'm just randomly making one equation, yz, xzk. And if they ask you whether to check whether the flow is steady and incompressible, what is to be done, beta? What is to be done? So what you can do, you can see that what is u is xy, and v is x square y square z square, w is xy plus yz plus xz, xy plus yz plus xz, right? So how we can see it, whether the flow is steady and incompressible? So you can go to this equation, del u by del x plus del v by del y plus del w by del z. So you can put the values of u, v, w in this equation and check whether this equation is being satisfied or not. Whether this equation is being satisfied or not. So if this equation is getting satisfied, okay, so then you can say the flow is incompressible and is steady. Now, is it fine to everyone? Please answer me, Vida. Is it fine to everyone, all of you? Please answer me, my dear. Can I have an answer on that, Vida? Are we clear in this? Please tell me, guys. Okay, so we can put the value of UVW in this equation and can obviously check whether the flow is compressible, incompressible, and is steady or not. Oh, sorry. Actually, I should have written incompressible here. Okay, not compressible. Only incompressible I should be writing here. Now, because rho is constant. Sorry, due to this technical glitch, I have written compressible. So it is actually incompressible. My mistake, Vida. My mistake. Okay, so whether the flow is incompressible and steady, how we can check? We can check by satisfying this equation, whether this equation is getting satisfied or not. So I am hoping that you will be able to take care of this. Now, what are the type 2 question here? What are the type 2 question here? What are the type 2 question here, beta? Now the type 2 question, what they give you, so they can give you the value of u, they can give you the equation of v, and they may ask you the equation to w. And they will ask, they may say that if u is this, v is this for steady and incompressible flow, for steady and incompressible flow, for steady and incompressible flow, find W. Okay, find the third component. Find the third component, guys. So how you are going to do it, beta? Can you guys do it or not? I hope we can very well do it, beta. Yes or no, beta? Please answer me. Right. So we can very well do it. Okay. So if I suppose, if I say that some value of u is given, some value of v is given, some value of w you have to find. Okay. So you can put it in this equation. Okay. So you will be getting this w by simple mathematics. Will you be able to do it or not? Please answer me, Vila. Please answer me. Okay. So let's make one problem out of it and we'll try that problem to see that we'll be able to take care of this kind of cases or not. Right, Buddha? Okay, just one moment. So is this clear up to this point or not? Okay, very well. Okay, okay, we'll get you a question now. Just one more moment. Okay, so we have u given as x square plus y square plus z square, and we have v given as xy square minus yz square plus xy, and you have to find w for steady and incompressible flow. So can you get me that, beta? For steady and incompressible flow. For steady and incompressible flow. So can you get me this w, beta? All of you? Can you guys get me this w? We have u, we have v. So what is this w, beta? For steady and incompressible flow, can you guys get me this w, beta? Please get me this w. Let's see if we can do it or not. Please go ahead. Please go ahead. How to do it? See, fluid kinematics is very much mathematics. You have to do differentiation, you have to do integration. You have to do differentiation and you have to do integration as and when required. So how we can solve this equation? So we have this u, v, and w. So del u by del x plus del v by del y, we know, plus del w by del z is equal to 0. So del u by del x we can put here. So del u by del x. So this is a partial differentiation thing. Okay, this is a partial differential thing. So when we put u here, so we'll be getting 2x, right, beta? Because we are differentiating partially with respect to x. And when we put del v here, so we will be getting, so partially differentiating with y. So 2xy minus z square, 2xy minus z square plus x, will be getting this, plus del w by del z. I hope it is fine to all of you. Just simply partially differentiating it. Right, beta? Please answer me. I hope it is fine. Okay, Vikram have given me some answer as well. So what we can do here, so we can write it like this. So we have it equal to 2 plus x, so 3x plus 2xy minus z square, right? And we can take it here. So we can write del W by del Z is minus, del W by del Z is minus of 3x plus 2xy minus z square. So now this is a differential equation, del W by del Z. Now you want to find this W. So what except integration we can do with this equation? So obviously we are going to integrate it. So when we are going to integrate it, we'll be getting minus 3xz plus 2xyz. So we are integrating keeping other parameters constant, but z. Okay, except the z, we are keeping all the variables as constant here. So this is going to be plus z cube by plus z cube by 3 plus z cube by 3. Is it fine, beta? Please answer me. Simple integration. Simple integration. Now, one thing to be take care of. So in this you have. So normally when we integrate, we add the constant of integration here. Normally when we integrate, we add constant of integration here. But in this case, as we have considered when integrating, we have considered x and y as constant. So we are going to have a constant in terms of x and y. So instead of writing c, which we are very much habitual of, we will be writing a function of x and y. So the right solution to this is w is equal to minus 3xz minus 2xyz plus z cube by 3 plus function of xy. Now, is it clear to everyone or not? Please answer me, beta. Will you be able to take care of these kind of questions or not? Please answer me, guys. Will you be able to take care of these kind of questions or not? Please answer me, beta. Please answer me. Will you be able to take care of these kind of questions or not, beta? I'm very hopeful that we can take care of these kind of questions. Yes or no, beta? Very nice. All right. So can we solve this gate question, please? Can we try this gate question? Can we try this gate question, please? Please go ahead and try this gate question. Please try it, beta. I'm very sure that you can do it. Please go ahead. It's a gate question, very easy question. We can do it, beta. Very, very easily we can do it. Please go ahead and do it, beta. The velocity field of an incompressible flow is given by, okay, velocity field of an incompressible flow is given by. So you are having this equation and you have to find a value of B2, whereas A1 and C3 is given to you. Okay, so A1 value, okay, Madhusudan have answered something, 2. Okay, very good, beta. So how we can do it? So this is what they are saying. He said this is a flow. This is a incompressible flow. So when this is an incompressible flow, what we can do? We can apply this equation for incompressible flow, right? This is the continuity equation for incompressible flow. Now, since the flow is incompressible, this equation must be valid for this velocity. Must be valid for this velocity. So del u by del x. So if I write del u by del x, it will be A1. If I write del v by del y, it will be B2. And if I write del w by del z, it will be C3. It will be C3. Now putting the value, so A1 is 2. A1 is 2, beta. A1 is 2 and B2 and C3 is 4 is equal to 0. So from here we can find the value of B2 and it is coming out to be 2. it is coming out to be 2. So now is it clear to all of you or not? Please answer me if it is clear to all of you. So I hope you will be able to deal with the questions when we have to play with the continuity equation to find or to check whether the flow is compressible or incompressible, as well as when we have one component and we have two component and third component is to be found, or this kind of a question in which some variable is to be asked. Now the next thing they are asking you in this second concept, so they are asking you about the acceleration. What? Acceleration. Now please tell me guys, acceleration is a vector or not? As similar to this velocity, acceleration is also a vector, right Buddha? Acceleration is also a vector. Agreed? Yes sir. Now since it is also a vector, so similar to velocity, it would be having component, it would be having component in both, or we must say it will be having component in all three directions as that of the velocity. So if I say the component of this acceleration in x direction is ax, in y direction is ay, in z direction it is az. Okay, so this is how we represent a vector, right? Ax, ay, and az. Now please understand this, in kinematics to find anything, so what else to be found? So in kinematics we have acceleration to be found, we have velocity to be found, which we already have done, we have acceleration, we have angular velocity, later we have vorticity, and then later we have the circulation, now to find any of it, the input data must be this. By using this u, v, and w, you can find the acceleration, you can find the angular velocity. Later on, you can find the vorticity and the circulation. I hope it is fine to all of you. Now, acceleration is axi plus ayj plus azk. Now, from uvw, how we are going to find this ax, ay, and az? So, I am going to write their formula. And I am hoping that with me writing it, you will be able to memorize it, right? So what is this ax beta? What is this ax? So ax means, so acceleration happens when velocity changes, okay? And as we have seen that there are two things, one is steady and one is uniform. So in steady, the things were changing with respect to time. So if velocity changes with respect to time, definitely there will be acceleration. And also we could see that the velocity was changing with respect to space. It can also happen if the flow is non-uniform. Getting my point, Bida? In that case, the acceleration will happen with respect to space. Okay, so consolidately, how we write the acceleration? So if we are writing the acceleration in x direction, so as x direction, what is the velocity in x direction? The velocity in x direction is u. So we may write like this. Please observe. Very simple. Plus del u by del t. Okay, plus del u by del t, and we have this u, v, and w. Okay, just write u, v, and w. Again, in y direction, what is the component of velocity? It is v. In y direction, what is the component of velocity? It is v. So again, writing del v by del x plus del v by del y plus del v by del z plus del v by del t, and we have, again we can write this way, u, v, and w. u, v, and w. Similarly, what is the component of velocity in z direction? It is w. Now, velocity change of this w velocity with respect to x, y, and z and t. Okay, and same way again we can write u, v, and w. U, V, and W. Now, in each of this equation, the first three things are representing you the changes of velocity. These first three things are representing you. These first three things are representing you the changes of velocity with respect to the space, because you have x, y, and z. So this is what we know as convective acceleration. This is what we call as convective acceleration. Now, what do we mean by that? This is what we call as convective acceleration, and what we mean by it. So the changes of velocity with respect to the space component, that is, what is the space component? X, Y, Z. This is what we call as convective acceleration. Now, please tell me one thing. I have a question here. If the flow is uniform, will there be any convective acceleration or not? Can you tell me yes or no? Repeating my question. If the flow is uniform, the convective acceleration will be there or not? If the flow is uniform, will there be any convective acceleration? Please tell me, beta. Please tell me, all of you, those who are watching me live here, please respond to me on that. Please answer me, beta, on that. What is your take on it? What is your take on it, beta? Gayatri is telling me no. What about the rest of you, beta? I can see many live students here. What about the rest of you, beta? So, guys, there will be no convective acceleration. Why there will be no convective acceleration, beta? Why there be no convective acceleration there? Why there be no convective acceleration there? Why? Because why there is no convective acceleration in that? Because just now we have learned that the things when are not changing with respect to space, that flow is uniform. So no change with respect to space. That means that acceleration is also not changing with respect to space. Okay. Okay. Now, so this first part of this acceleration, what we call as the convective acceleration, and the second part is what we call as temporal or local acceleration. Temporal or local acceleration. And as you can see through this formula, that this part of acceleration happens to be when the velocity changes with respect to time. Yes, Madhusudhan. Okay. So if velocity is not changing with respect to time, obviously there will be no temporal or local component of acceleration. Right, beta? Please answer me if it is clear to you or not. So this is temporal or local acceleration. Okay, so what is this temporal or local acceleration? So that part of acceleration which represents the changes of velocity with respect to time is the temporal or local acceleration, and the part of acceleration which represent the changes with respect to space is called as convective acceleration. Now please tell me, if the flow is steady, will there be a convective component of acceleration? If the flow is steady, only will there be any Convective acceleration, please give me yes or no. बताइए. Please give me a yes or no on this. If the flow is steady only, will there be a convective acceleration? So yes, sir, there will be a convective acceleration because in steady flow, but in steady flow, changes do not happen with respect to time. That means the component of this acceleration that happens to be with respect to time will not be there. So, but no temporal acceleration. So, in this case, there will not be any temporal acceleration. So, I hope it is fine to everyone, beta. I hope it is fine to everyone. Right, beta? Right or not, beta? Okay. So, now let's do one more question. Okay. Okay, let's try this one. Let us try this one, beta. Please go ahead. Let us see if we can do it or not. Please go ahead. Let us see if we can do it or not. Please go for it. I'm very sure that we'll be able to do it. Please go for it, beta. So what does this first part of this question say? So this is the question I have giving you to explore the concepts or to revise the concepts. So the fluid flow field is given by. So obviously we can first of all the first thing. So see the pattern of the question. The input data will be this velocity components. Okay. So v is equal to x square I x square y I plus y square z j minus 2xy z plus yz square k. So what is the u we are having? U is x square y. What is the v we are having? It is y squared z. And what is the w we are having? It is minus of 2xyz plus yz square minus of 2xyz plus yz square. Right, beta? Right, beta? Now we have to see whether it is a case of possible steady incompressible fluid flow. So for that, we have to check this continuity equation, right? Okay. So what is this del u by del x? Del u by del x is coming out to be 2xy plus del v by del y. It is 2yz. It is 2yz and del w by del z. Del w by del z. So it is going to be plus. Okay. So del w by del z is minus of 2xy minus of 2yz. So as we can see, it is 2xy minus 2xy plus 2xy is 0 plus 2yz minus 2yz is 0. So that means it is a steady incompressible flow. So what we can say, it is a steady and incompressible flow, right, beta? It is a steady and incompressible flow. Now we have to find the acceleration at the point 213. Okay, we have to find the acceleration at 213. So what is this point representing? 213. So this is the coordinates of x, y, and z. Okay, x, y, and z. So what can be done, beta, here? What can be done? So if in case, so first of all, what we have to do, we have to firstly find AX, then we have to find AY, then we have to find this AZ. Are you getting my point, Beta? We have to find this AX, we have to find this AY, and we have to find this AZ. So how to find AX, Beta? How to find? So already we have seen the fluid is steady and incompressible. So there will be only convective component of acceleration. So we can write it like this: del U by del X. So see, remember how to write it. X, the velocity component in X direction represented by U. So you can write U here at all places and differentiate it with the space coordinate. This is U, this is V, this is W. Okay, so we can find this AX from here by putting the value of U. So U is X square Y here. Okay, so let me write the formulas first. So del V by del X plus del V by del Y. I hope you learned to see how to write the formula. Okay, and here it is U, here it is V, here it is W. We have the Z, that is del W by del X plus del W by del Y plus del W by del Z, and we have this U, we have this V, and we have this W. So in these equations, we can put the value and do the necessary differentiation, and we can find out what is the AX, AY, and AZ. So I'll be finding this AX for you. So U is what? Just do not make any mistake here. So U is X square Y. Now differentiating X square Y with respect to X, so it is 2xy. Plus we have V, that is Y squared Z, Y squared Z, and del U by del Y. So we are having X square, and this U, no function of Z is there, so it is going to be 0. It is going to be 0, right, Buddha? It is going to be 0, right, Buddha? Right, Buddha? So what we'll be getting, Buddha? What we'll be getting? So what we can do now? What we can do now? So we can put the value of this point 213. So putting 2 instead of X, right, Buddha? Yes or no, Buddha? Please answer me. Now we can put this. So if we put it, so we can directly put it here. What we can put it here? So X is equal to, so this is the coordinate system. So X is equal to 2, Y is equal to 1, Z is equal to 3. So by putting the values of X, Y, and Z here, what we'll be getting? By putting the value of X, Y, and Z. So we are having 2 square into 1, that is 2 into 2 into 1 plus Y squared Z, that is 1 into 3 into 2 squared, that is 4. So we are going to have 4, 4, 16 and plus 12. So we are having 28 units, right? So this is your AX. This is your AX, beta. This is your AX. Is it fine to everyone? I hope it is fine to everyone. Now, similarly, you can find this AY by using the formula and then by putting the value. So when you find this AY, you will be having it as minus 3, and when you find this AZ, when you will be finding this AZ, you will be having, my dear, 123. You will be having 123 units, right, Buddha? Right, Buddha? So at this, so at these point coordinate, what will be the velocity and acceleration? So for finding the velocity, directly you can place the value of X and Y in the equation given in the question. So I have calculated this acceleration for you. So you can place it back in the equation. You can place it back in the equation. And if you have to find the resultant, what you can do, what is the resultant acceleration? So how we find the resultant of vectors which are perpendicular to each other? So we can simply square them like this, right? We can simply square them like this. So I hope this is fine to everyone. Please answer me, Vida. Please answer me if it is clear to everyone or not. Please answer me, guys. Please answer me. Will you be able to take care of the kind of questions like this, beta? Will you be able to take care of these kind of questions or not? Let's do one gate question now. A lot of questions you will be finding in the previous year gate questions, and I am hoping that in the upcoming years also you will be getting these kind of questions again and again. So these are the very important concepts of the fluid mechanics, very important for both mechanical and civil engineering students. Please go ahead. This is a gate PYQ. Let's solve it. Let us solve it, beta. Please go ahead. Please go ahead. Let us see if we can do it or not. Please go ahead, beta. Acha. Okay, okay. Is it fine now, beta? Is it fine now? I hope it is fine now. Vikram, now everything is visible. I am hoping that, beta. Please go ahead. Now do it. Now let us do it, beta. Very simple question. Again of the same pattern. Let us see if we can do it or not. Please go ahead. Any answer? Okay, so Vikram have given me some answer. What about the rest of you, beta? What about the rest of you? I'm very hopeful that you can do it. Okay, so Madhusudan have also given the C option. Very well. Okay, guys, so I'll do it. So now for a steady flow, the velocity field is this. Okay. So first of all, this is U and this is V. No component of W. No component of W. So it is a two-dimensional flow. Sir, but sir, by using the continuity equation, we can find the W. Why we are not doing that? Some students ask me that. So here, better see that the coordinate system, only the coordinate values of two are given, only x and y coordinate values are given. So that is obviously means it is a two-dimensional system. Otherwise, the z coordinate is also given. So if in this kind of a question the z coordinate is also given, then first of all you must find the w, that is the third component of velocity, and then you move to the acceleration. But here we can do it very good, Madhusudan, very good, Naga. Okay, so now obviously we have this u and we have this v. So we can find the acceleration. So again, the flow is steady. So we have this acceleration, only ax and ay will be there, and it is going to be equal to del u by del x plus v del u by del y. Okay, so let's just find it here. So what is this u? It is minus x square plus 3y. Okay, and what is this? So it is going to be minus 2x, right, brother? And this is v, so v is 2xy, and this is going to be 3, right, brother? This is going to be 3. So we can take care of it. How? So we can see that it is coming out to be minus minus plus 2x cube, then minus of 2xy, then minus of 2xy, sorry, 6xy, 236, that is 6xy. Please take care of the calculations, my dear. Plus 6xy. So we are only having this 2x cube. So what is the value of this x? It is 1. It is 1. So basically we are having it as 2. So the component of acceleration in x direction is nothing but 2. Very good, Gayatri. Okay, it is 2. Is it correct, beta? Please take care of the calculations. And this ay. What is this ay? So ay is u del v by del x plus v del v by del y. So what is this v we have? So v is 2xy. So u is minus x square plus 3y, and del v by del x. So del v by del x is 2y. Okay. Plus v. So v we are having as 2xy, and del v by del y is 2x. Okay. Del v by del y is 2x. So we are having 8x again. So some component we see, no component is getting cancelled out. So we are getting minus 2. We are getting minus 2 of x square y plus 6y square plus 4x square y plus 4x square y. So we are having 2x square y, 2x square y. We are having it as 2x square y plus 6y square. Now we can put the value of x and y. So x is 1 and y is minus 1. So we are having minus 2 plus 6, that is 4. That is 4. Right, beta? That is 4. Okay, so now ay is 4 at this value. So ax is 2, ay is 4. So the resultant would be 2 square plus 4 square. So basically we are having 4 plus 16, that is 20. That is 20. So that is nothing but 2 root 5, because you can write it as 4 into 5. So it is 2 root 5. That is C option. That is C option. Now tell me one thing, beta. All of you give me this confidence that if we see this kind of a question of acceleration, we'll be able to take care of it. So this is the second concept of the day. The first one, to take care of the velocity for a steady incompressible flow. The second concept was of to take care of this acceleration. Will you be able to do it, beta? Many questions you will be seeing in the GATE examination out of this concept. Please tell me, beta. Please tell me, beta. Will you be able to do it? Please answer me. Very nice. Now coming to the third concept of the day. Okay. Okay. So sometimes, beta, they ask you about rotational and irrotational flow. About rotational and irrotational flow, right? Rotational and irrotational flow. So how to see whether the flow is rotational or not? So for that, you have to get the angular velocity component of the fluid flow. Okay, so we have seen this V, that is the linear velocity component. We have seen this acceleration. So we now have to see this W. W here is your omega. Okay, so we can write it like this, omega. Okay, so omega W somewhat look like this when we write, but this is your omega. Getting my point? The angular velocity component. So again, angular velocity is also a vector. Yes or no, beta? So when it is also a vector, we can write like this, the same way. Okay, the same way. Now, what is this omega x, omega y, and omega z? So I'll be making it easy for you to memorize. Okay, and you anyway have to memorize it. So see how we can write. We can understand this pattern: x, y, and z. So after x, what is there? Y. After y, what is there? Z. Okay. Now the component of velocity in the direction of y is v. You can take v here. The component of velocity in the direction of z is w, and put a half in there. Okay, outside. Again, how you can write it? So after y, what we have? We have z. After z, what we have? We have x. Okay, if you follow this pattern, x, y, z, x, y, z, x, x, y, z, x. This is how I remember this. Okay, after so many years. Okay, like after nine years back, 9 years back, I have seen all this thing, but still I remember this because I make this pattern. Okay, so this x, the component of velocity in the direction of x, it is u. The component of velocity in the direction of z, it is w. Now z, after z, what we have? We have x. After x, what we have? We have y. The component of velocity in the direction of y is v. The component of velocity in the direction of x is u. So we can write this way. So we can write this way. So del v, half del v by del x minus del u by del y. Is it fine, beta? How we have written it? How we have written it? And what will be the input data again? Again, the input data will be the same way. That is ui plus vj plus wk. That is wk. Getting my point, beta? Getting my point? Okay. Okay. So this is the C, rotation. This is the rotational vector, the angular velocity. So I hope we are agreed to this point that rotation happens about some axis and in some plane. Right, beta? Right, beta? Please answer me. So sometimes to confuse you, so this omega x is basically the rotation vector, rotation in yz plane, remember. Okay, it is the rotation in yz plane. Rotation always happens about the axis. Getting my point? Rotation happens about the axis and in the plane. So if we say the rotation is happening about axis x, it means it is taking place in the plane yz. About y, it is in the plane xz, in the plane xz, and it is in the plane xy. So normally guys, they, when we are given a two-dimensional system, when we are given a two-dimensional system, normally the system is given to us in the x and y plane. So in the x and y plane, if we have to check the velocity vector, we must be finding omega z, right, beta? Now, for the flow to be irrotational, for the flow to be irrotational, now for the flow to be irrotational, omega x, omega y, omega z all must be 0. Now obviously in two dimensions we will having only one component of angular velocity. So for two-dimensional flow, only that component must be 0 for saying the flow to be irrotational. Now guys, will you be able to take care of this or not? Please answer me. Bolo, if somebody is asking you to check whether the flow is compressible, rotational or irrotational, will you be able to deal with it or not? Please answer, Vida. Will you be able to deal with it or not? Please answer, Vida. Please answer me. Okay, so let us do one question here. Let's do one question here. So we have V is equal to 8x cube I minus 10x square yj minus 10x square yj. Okay, 8x cube I minus 10x square yj. Okay. Now tell me whether it is rotational or irrotational. Rotational or irrotational. Let's try it. Please go ahead and tell me whether it is rotational or irrotational. Please go for it. Please go for it. Please go for it, beta. Tell me whether it is rotational or irrotational. Krishna, we have to check it, beta. So how we can do it, beta? How we can do it? So we can see. So this is again, it is given as U, it is given as V. It is given as U and V. So what is this U? U is 8x cubed. V is minus 10x square y. Just don't let go of this minus sign. We have to compare with this. Ui plus Vj. So while we are comparing with this beta, while we are comparing with this, care must be taken that you do not ignore this minus sign. Okay, beta? So we have this u, we have this y. So what is this? So we have this xy plane. Obviously, when we have this u and when we have this v, so we are talking in the xy plane. So the rotational vector must be about this third axis, that is z. So what is this omega z? What is this omega z? So after z we have this x. After x we have this y. So component of velocity in y direction, component of velocity in x direction. Okay, so what we can do? Half del v by del x. So we have it x minus 20 xy. Right, but del v by del x is minus 20 xy and del u by del y is 0. So we are having is at minus 10 xy, which is certainly not equal to 0, which is certainly not equal to 0. So this flow is what? This is rotational flow. This is rotational flow. So will you be, no problem, Krishna. Please take care in the next time. Okay, because see, these are very important concepts and continuously this is getting asked in the GATE examination. And I know that we are serious student and we want to crack this examination, right? Okay. Okay, and what this series is meant for? So this series is meant for making you go through these important concepts as quickly as possible, right, Buddha? Right, Buddha? So in kinematics, according to me, these were the most important concepts. Okay, these were the most important concepts. Now, else to this concept, we have to see the vorticity by our own. Last session also, I told you guys that we are here dealing with, or not just making it giving you a revision of the most important concept, that but it doesn't mean that you leave every all the other things. Okay, so what else to be studied? Vorticity, circulation, potential function. Okay, stream function, right beta, and vortex motion. So all these things are to be studied by our own. Getting my point? Not, we are not going to cover it in today's session. Now, concept 4 for the day in the section of dynamics. As this session name says, kinematics and dynamics. Now, fourth concept, and perhaps the most important, that is our great Bernoulli's equation. Fluid mechanics without this equation is kind of incomplete, and again you will be finding many questions of this point in the gate examination. So what are the assumptions to write the Bernoulli equation, beta? What are the assumptions? Sometimes they may ask you the assumptions also, and they kept asking you this previously also. So what are the assumptions that we have here, beta? What are the assumptions that we have here? So the assumptions are, first is steady flow, second incompressible, irrotational, and along a streamline. So these are the basic assumptions of fluid of Bernoulli equation. Is it fine, beta? I hope we all are well aware of it. And what does Bernoulli equation says? So if we have a cross section like this, okay, so first of all, I'll be explaining you. So what is this Bernoulli equation? P by rho g plus v square by 2g plus z is equal to constant. This is how we write a Bernoulli equation. The most standard form that we very frequently use. Yes or no, beta? Yes or no? Okay, in terms of the energy per unit weight, right, beta? Or how we apply it. So let's suppose we have a condition like this, okay, and we have, let's suppose, so what is this z? This is the datum. This represents the factor of this height, pressure and velocity. P and V obviously represent the pressure and velocity. So if I say this section as 1 and this section as 2, this section as 2, and we have to apply the Bernoulli equation between section 1 and 2, how we can do it? So P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2 plus Z2. This is the ideal Bernoulli equation. And a lot many questions are being asked. A lot many questions are being asked from this topic in many years previously also, and in the later years also this will be getting asked to you. This is going to be asked to you. Now if I say, now please understand this, if I say, so see in gate examination what they do, so Bernoulli equation we all are aware of. I hope we all must have seen this equation, because this is equation which is very helpful in getting us past the semester examination also, right? Okay, now if they frame the question like this, that this is the section, this is the section, so they do frame the question like this also, but mostly they will frame a question whose packing is very heavy, right? What I mean by mean to say, let me show you one question. Let me show you one question of gate examination. Just one moment. Okay, so here we go. So this is the PYQ, previous year gate question. This is the previous year gate question, beta. This is the previous year gate question. I hope you can see it. I hope you can see it. Okay, let me. Okay, right. So can we try to solve this question, beta? Can we read this question and can we try to solve it? This is the previous year gate question. I hope you can read this. Can we read this, beta? This is a PYQ, previous year gate question. So a syringe with a frictionless plunger contains water and has its end 100 long needle of 1 diameter. The internal diameter of the syringe is 10 The internal diameter of the syringe is 10 Okay, and the needle is 1 Please go for it, Buddha. The internal diameter, everything is given. Just try to solve this question. So this is when I do it. This is a simple question of Bernoulli equation, but they packed it very heavily. Because see, when as a student, when we see this kind of a question, okay, syringe is there. Oh, how to solve a question? And the syringe is there. We never have solved the question of syringe. So they are just trying to make a delusion in your mind that this is not going to happen in your efforts. Okay, so it is not like that, Buddha. It is definitely not like that. Okay, it is certainly not like that. Please go ahead. Let's try to solve this question, Buddha. Let us try to solve this question. Any answer? So what does this question say, beta? A syringe with a frictionless plunger contains water has at its end 100 long needle of 1 diameter. The internal diameter of the syringe is 10 water density is 1000 kg per meter cube. The plunger is pushed in at 10 per second and the waters come out as a jet. Assuming idle flow, the force F in Newton required on the plunger to push out the water. Required on the plunger to push out the water. So what we have, beta? What we have? What we have? So we have to find the force. We have to find the force. Okay, on this plunger. Now, from Bernoulli equation, we can find the pressure, right? But from Bernoulli equation, we can find out the pressure, right, my dear? Okay, from Bernoulli equation, we can find out the pressure. Now, what is to be multiplied in the pressure in order to make it? What is to be multiplied in the pressure in order to make it? In order to make it uh, the force. So obviously we have to multiply the area. So we have to find the force on the plunger. So if by any way or by any means we can find the pressure at this region, let's suppose this is 1. If we can find the pressure at this point and multiply it with area, we can certainly find. We can certainly find what? We can certainly find the force here. Right. So let's suppose this section is 1, this section is 2. Now, obviously, a Bernoulli equation, whenever we apply between two sections. So, if I apply the Bernoulli equation between two sections, so it is going to be P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2, right? But now you see the section 2 I have taken is in atmosphere. So we can cancel it out. This is 0. This is 0. The datum is same. So how you can cancel this out? Because this is atmospheric pressure. Nah? When it is outside, it is atmospheric. So in fluid mechanics, we are talking about the gauge pressure. So atmospheric pressure can be taken out to be 0. So this is going to be 0. Okay, so this is P1 by rho g. This is P1 by rho g. So we are interested in finding this P1. This is 1000 into 9.81. What is the velocity here? So velocity at point 1 is 10 meter per second. So it is 0.01 square, because 10 mm per second is 0.01 meter per second into 2 into 9.81 is equal to V2 squared by 2. So do we have this V2? No, we do not have this V2. So first of all, we have to find this V2. Now applying the continuity equation for incompressible one-dimensional flow, so it is A1 V1. So whenever, remember this, whenever we have to apply the Bernoulli equation, continuity equation is getting applied at as many times, right? So we have this A1 V1 as A2 V2. So what is the area 1? It is pi by 4 into 10 square into V1. V1 is 10 mm per second, and A2 is pi by 4 into 1 square into V2. So we can cancel this out. We can cancel this out, and V2 will come out to be 1000 mm per second. 1000 mm per second. So from here, we can put it here. So 1000 mm per second, that is 1 meter per second. So 1 square by 2 into 9.81. So from this equation, you can find this P1. And what is this force? So it is going to be pi by 4 into, so what is the diameter here at the plunger? It is 10 mm. So it is going to be 0.01 whole of a square. 0.01 whole of a square. Is it fine, beta? And when you do it, you will be getting 0.04 Newton. Is it fine, beta? Please tell me yes or no, beta. Will you be able to solve it? Can you check the answer, beta? If you want, you can check the answer as well. Please go ahead. Please check the answer of it. Please do the calculation and tell me whether you are able to understand the concept or not. Please answer me. Please answer me, beta. Is it clear to everyone or not? Please answer me, beta. So what is the concept here, beta? So while applying the Bernoulli equation, first of all, do not get feared of the packing of the question. Okay, they pack the question in fancy ways, like a syringe is there. Sometimes they apply a spring there. So don't get afraid of it, right? Don't get afraid of it. Please try to do the way I told you, right, beta? Right, beta? Please answer me. Okay. Now, this is the fourth concept of the day. Now, I'm going to give you one last concept for the day. So, we'll call it the fifth concept. Okay. So, sometimes what they do, they use a manometer to tell you the pressure difference. They use a manometer to tell you the pressure difference. So, let's see it with the Venturi meter. So, let's suppose we have a Venturi meter. Let us suppose we have a Venturi meter. So Venturi meter is a flow measurement device which has one throat section, like this. If I apply the Bernoulli equation here and here, if I apply the Bernoulli equation, so let's suppose this is 1, this is 2. So this is also known as the short section because the Are Shivam, don't think that way, beta. Kinematics is not removed from the GATE syllabus. Don't worry about it, beta. Okay, it is not. Without kinematic, without continuity equation, is it possible to learn the Bernoulli equation or the dynamics? Please tell me. It is not possible. When they write the dynamics, kinematics is already there. Similarly, they have not removed it. They have not mentioned it. Like manometer is also not mentioned. Right, it is not in the last session also I clarified this thing. Without continuity equation, without kinematics, dynamics is not possible at all, right? In any subject, not only in fluid mechanics. Okay, if engineering mechanics also you study, you have to study the kinematic first, then go for the dynamics, right? Okay. So we have, let's suppose we have to apply the Bernoulli equation in between these 2 points. So what we can say, P1 by rho g plus V1 square by 2g is equal to P2 by rho g plus V2 square by 2g. V2 square by 2g. Now from here we can write P1 by rho g minus P2 by rho g is equal to V2 square by 2g minus V1 square by 2g, minus V1 square by 2g, and by continuity equation we also know A1 V1 is equal to A2 V2 is equal to Q, right, beta, is equal to Q. Now, beta, this is I am replacing it. P1 by rho g minus P2 by rho g is equal to H. And if I write like this, I hope you won't mind me writing like this. So A2 square into 2g minus it is Q square upon A1 square by 2g. Okay, so we can write from here Q square is equal to root, or we can write directly Q here. So if we solve this equation, we can find that Q is root 2gh A1 A2 upon root over A1 square minus A2 square. Is it fine to everyone? Beta, please answer me. Just by solving this equation, can we write this way? So this is how we can find, or this is the general formula of a Venturi meter. And since we are using the Bernoulli equation, which is having some assumptions, so we call it theoretical discharge. Now to find the actual discharge, we use this CD, that is coefficient of discharge. That is coefficient of discharge. Now the question is, what is this H? So can I write this H is pressure head difference? Now remember this. This is pressure head difference. So in the last session of this series, we have seen the fluid statics, in which we have seen the pressure measurement. And in that, we have seen this hydrostatic law, that is P is equal to rho GH. And we have spoken about that the pressure is represented in terms of the heads of liquid also. So this H is pressure head difference between 1 and 2, pressure head difference between 1 and 2 in terms of fluid flowing through pipe. Right, beta, or wrong? Right or wrong? So H is the pressure head difference between 1 and 2 in terms of the fluid flowing through the pipe. Okay, so we have the section 1, we have the section 2. So this H is representing the pressure head difference. Now, in the last session, we have seen that this pressure head can be measured by using the manometers. So if I apply a manometer in here, like this, if I apply a manometer in here like this, and in manometer, obviously we have some fluid, some manometric fluid, which is having the different density compared to the density of the fluid flowing inside the pipe. So let's suppose here the density is S and the density of this fluid is Sm. So this is the difference of it as x. So what we require h, which is h1 minus h2, which is h1 minus h2. So how we can do it, beta? How we can solve it? So last session, what we learned to write the Manumetric equation, right? Those who have not seen the previous to this session, please go ahead and see it. Okay, so if I start writing from one, how I can write it? So what concept we have seen in the last GATEvantage series, that one, we can change everything to water. So let's suppose the pressure in terms of water at this section 1 is H1W. We are moving downwards. We are moving downwards. So let's suppose this is Y, or just not. So this Y is here and this Y is going up. So if you write it, it is going to cancel out. So I'm not writing it. So from here directly I jumping. Chalo, let's write it. Otherwise you will get confused. So can we write Sy plus Sx? Okay. Okay, then we reach to this point. Now in the same fluid, from this point to this point, we need not to write anything. Now we are moving up by the distance x. So when we move up, we subtract, then we again move up to y, and we reach this 2 points, so h2w. So this sy is getting cancelled out. So this h1w minus h2w is equal to sm, or we can write x sm minus s. Can we do like this or not? Now this h1 minus h2 and h1w minus h2w are same or not? No, they are not same. This is in terms of the fluid flowing through the pipe. This is in terms of water. Now how we convert any pressure in terms of any head in terms of water? Simply by multiplying it with density. So if I multiply it with S, it will become N H1W minus H2W. So it is X Sm minus S. So what finally we can write? So from here you will see this famous formula. H is X Sm by S minus 1. So if you transfer this S on the right hand side, you will be getting this. So this H1 minus H2, that is H, is x sm by s minus 1. Very, very important concept for you. And this is getting used, this formula is getting used in any way whenever we have manometer applied to, whenever we have manometer applied in the problem. Is it fine, beta? Please answer me. Will you be able to take care of it? Please answer me. Please answer me, beta. Is it fine? So let's do one question here. Okay, let's try it. Let's try it. Let us see if we can do it or not. Very good, Bida. Let's do it. Let us see if we can do it or not. Please go for it. I'm very sure that we can do it, Buddha. So how we can solve it, beta? So we have a horizontal Venturi meter with inlet and throat diameters of 30 centimeter and 12 centimeter is used to measure the flow of water. So the reading of differential manometer connected to the throat is 20 centimeter of mercury. So what is this axis 20 centimeter and what is this SM? It is 13.6. These two informations are given whenever we have this mercury. Whenever we have this mercury, so for mercury, if nothing is given, we consider the specific gravity or density is equal to 13.6. Okay, so what is the rate of flow? So we know Q is CD root 2GH. So since CD is given, A1, A2, we just derived this formula upon A1 square minus A2 square. So what is this A? Please take care of the unit beta. So what is this A? So A is pi by 4 of D square. So centimeters, so that is 0.3. What is this A2? It is pi by 4 into 0.15 square. This is your A2 beta. This is your A2. What is this H? H is X SM by S, so 13.6. What is flowing inside this? So water. Water specific gravity is 1. SM by S minus 1. So X is 20 centimeters. So we can put it in terms of water, oh sorry, in meters, so it is 0.2 into 13.6 minus 1, that is 12.6. So we have all the data here. CD is also given in the question. CD is 0.98. I am very sure when we put this here, we'll be getting the discharge. We'll be getting the discharge. So this fifth concept for the day is clear or not? Will you be able to take care of the questions in which, will you be able to take care of the questions in which, beta, we will be given in the questions, we will be given this this thing. Please answer me, beta. Is it fine to everyone or not? Please answer me, my dear. Please answer me, my dear. Please go ahead. I hope you understood this concept, beta. So dynamics, this is just one most important concept I felt that Bernoulli equation is getting frequently asked. After it, there are so many things. We have pipe flow, we have compressible flow, all that is dynamics only, beta. Okay. So again, I'm clarifying this. So we are dealing with the important concepts only, but we are not saying you to leave the every other concept. Okay. So I hope guys you like this video and you find this session useful for you. The live students, thank you very much for joining us in this live session today also and in the previous session also. Okay. So for any query, you can call us, you can visit us and do like and subscribe the channel and we'll see you soon, very sure in the some other video. Okay, so meanwhile, do not forget to subscribe the channel. Please do share it with your friends. Please spread the word. We are trying everything to help you guys. Okay, in this gate examination. Okay, Vikram. Okay, I am very sure that you can get it the answer. Thank you, Anagu. So, Adaga, sorry. So thank you very much, guys. Thank you very much and very best of luck for the GATE examination and hope to see you again. Do not forget to like and subscribe and share with your friends.